In this lesson, we want to talk about symmetry, and we also want to talk about even and odd functions. So what we want to do is start out by talking about symmetry with respect to kind of the x-axis, the y-axis, and the origin. This is going to lay the foundation for us to talk about even and odd functions. So we're going to start out by talking about graphs that are symmetric with respect to the y-axis, okay, the y-axis. So this will occur whenever replacement of x with negative x yields the same equation. So let's look at an example. So here we have f of x equals x squared. And of course, this is our squaring function. We've worked with this a lot. We can visually see that this is symmetric with respect to the y-axis, right? The way you can think about this is, let me highlight the y-axis. If I folded kind of the right side of this graph over the y-axis, you would see that the right side and the left side would match up perfectly, okay? And the reason for this is, for any given y value, you're going to have two x values that are kind of associated, with the one exception to that being 0, okay? So that's because of this kind of squaring operation here. Let's say I take this point here, and I take this point here. So this point on the right, this is going to be 2, 4. This point on the left is going to be negative 2, 4. So where does this come from? If I plug in a 2 and square it, I get 4. If I plug in a negative 2 and square it, I also get 4. So because of this squaring operation, essentially I can have two different x values that produce the same y value, okay, a negative and then a positive. But that doesn't work for 0. So this guy down here, this y value of 0 is only kind of associated with an x value of 0 because 0 squared is just 0, right? So that's the only exception to that guy. Every other y value is going to be associated with two different x values, but the rule still works with 0, right? If I put a negative in front of 0, I still get 0. Now, in a lot of cases, you're not going to have a graph. You're going to have something kind of complicated. You might not have time to graph, or you might not be able to. So you want to kind of go through a process where you replace the x with the negative of x, and you see if you get the same thing. So let's do that on a fresh sheet. So if I have f of x, and this is equal to x squared, and what I want to do is see if f of negative x, that just means I'm plugging in a negative x for x, if that's equal to x squared. Okay, is that the same? So what I'd have is the negative of x being squared. Now, one thing I want to call your attention to, I wrapped this in parentheses. Whenever you substitute in for a variable, you want to wrap whatever you're plugging in inside of parentheses. So I'm wrapping my negative x inside of parentheses, and then I'm squaring it. Okay, that's the proper way to do that. If you make a mistake on this and just say it's negative x squared like that, well, this is negative 1 times x squared. That's going to give you the wrong answer, okay? So you want to wrap it in parentheses and then square that, okay? So really what I can do is I can break this up, and I can say this is negative 1 times x that's being squared. Now, hopefully you remember your rules of exponents. If we have a times b, and this is squared, this is a squared times b squared. Same thing here. I have negative 1 times x. These two guys, these factors, are both being raised to the second power. So what I can do is I can split this up and say I have negative 1. Again, that whole thing is being squared, so I'm wrapping it in parentheses. And then times I have my x squared. We know that negative 1, that amount squared is just 1. So that would be 1 times x squared, which of course is just x squared. So these two guys are the same, right? If I replace x with negative x, I end up with the same guy. So we can say that it's symmetric with respect to the y-axis. Later on in the lesson, we'll hear this called an even function. Okay, when this kind of property holds, it's called an even function, but we'll get to that later on. All right, so another good example of kind of an even function or a graph that's symmetric with respect to the y-axis is this f of x equals the absolute value of x. Again, if I kind of highlight the y-axis, you can see that if you folded the right side over the y-axis, it would perfectly line up with the left side. So again, we can prove this pretty quickly. We can say that f of negative x is equal to what? Well, if I plugged in a negative x there inside of the absolute value bars, again, I have another rule with absolute value. If I have, let's say the absolute value of a times b, this is the absolute value of a times the absolute value of b. Okay, by rule. So I can split this up and say that it's the absolute value of negative 1, right? Because this is really just negative 1 times x. then times the absolute value of x. Okay, that's all that would be. The absolute value of -1 is always 1. So this is just the absolute value of x. So these two are the same. So again, we've proved that this guy is symmetric with respect to the y-axis. All right, so now let's talk about symmetry with respect to the x-axis. So this is going to be the same concept, but now the x-axis is going to kind of cut the graph in half. Again, where each half is just a mirror image or reflection of the other. Now, if a graph is symmetric with respect to the x-axis, okay, with respect to the x-axis, then replacement of y with -y yields the same equation. One thing I'm going to tell you in advance is that if a graph is symmetric with respect to the x-axis, for a given x value, you're going to have this y and -y that are kind of associated with it. So we know that from our definition of functions, this will not be a function, right? It will fail the vertical line test. Now let's look at an example of this. So we have y squared equals x, right? We're used to seeing y or f of x is equal to x squared, and we saw this earlier, but now we're seeing something a little bit different. So now I plug something in for y, I square it, and I get a result for x. So each x value now is going to be associated with two different y values, one positive and one negative. The only exception to that, again, is with this kind of 0 here. And that's because if I plug in a 0 for x, well, I know that what squared would give me 0. Well, there's only 0 that could do that, okay? But for every other situation, let's say I choose an x value of 9. Okay, so that's here and then also here. So I know that a y value of 3 squared would give me 9, and then also a y value of -3, if that's squared, it would also give me 9. So that's why we have this kind of scenario going on. But you can see that kind of the vertical line test would fail here, right? If I drew a vertical line here, it hits here and it hits here. So this is not the graph of a function, but it is symmetric with respect to the x-axis, right? This guy is going to cut it in half, where again, if we folded kind of this top part over the x-axis, it would perfectly line up with this kind of bottom part below the x-axis. Now, how do we prove this? Again, we plug in a -y for y, and we see if we get the same equation. So it's the same kind of concept here. If I plugged in a -y and I squared it, well, we saw earlier, if I square this guy, I'm going to get +1. So really, this ends up just being y squared equals x. Same thing as I have here. So that's how we know that we have a graph that's symmetric with respect to the x-axis. All right, let's take a look at another one. So now we have x equals the absolute value of y. Again, this is kind of the absolute value function we're used to, just turned on its side. Just like we saw the parabola we're used to turned on its side. So for this guy, I'm plugging something in for y. I take the absolute value, I get something for x. So in other words, if I take a negative and I plug it in, I get a positive. If I plug in a positive, I keep the positive. If I plug in 0, obviously I get 0. So with the exception of this point right here, which is 0, 0, anytime I plug something in for kind of y, I could plug in the opposite thing for y and still get the same x. So here's a good example here. We have 4, 4, and then we also have 4, -4. Okay, so 4, -4, and this is 4, 4. Okay, so if I plug in a 4 for y, take the absolute value, I get 4. If I plug in a -4 for y, take the absolute value, I also get 4. So that's what's creating this kind of effect here. We know this is not a function because, again, it would fail the vertical line test, but it is going to be symmetric with respect to the x-axis because, again, if I plug in a negative y in the place of y, we know that this guy would end up being just x equals the absolute value of y, right? Because this guy right here, I could really just split it and say it's the absolute value of -1 times the absolute value of y. The absolute value of -1 is just 1. So I end up with this guy, which is exactly what I have right there. All right, let's take a look at one more of these. So this guy is x plus 2 quantity squared plus y squared equals 25. So we see this is the graph of a circle, and it's not symmetric with respect to the y-axis. We can see that, right? If I took kind of this guy and highlighted the y-axis, we can see that it's got less on the right side than it does on the left side. So if I folded this over the y-axis, those graphs would not match up. Okay, so it's not symmetric with respect to the y-axis, but it is symmetric with respect to the x-axis. You can see if I folded kind of the top part over the x-axis, I would end up with something that perfectly matches up with the bottom part. Again, we can prove this by just plugging in a negative y there. But you can see because of this exponent here, that this guy, if it got squared, it would give me the exact same thing. So the equation wouldn't be changed. So that's how we know that it's symmetric with respect to the x-axis. All right, now the last one we're going to look at is when a graph is symmetric with respect to the origin. So this one's a lot more difficult to kind of look at and see visually. But essentially, if we replace x with negative x and y with negative y, and we end up with the same equation, we have symmetry with respect to the origin. So what you're going to find is that on a given graph, if you have an x comma y, then you're going to have the negative of that x and the negative of that y on the graph. So let's look at an example. So we have f of x equals x cubed, or our cubing function. This is the typical example you see when you first talk about kind of an odd function or a function that's symmetric with respect to the origin, or just a graph that's symmetric with respect to the origin in general. So we can really write this as y equals x cubed. And what I can show you is that, again, if I replace x with negative x and y with negative y, I end up with the same thing. So if I plugged in a negative y and I plugged in a negative x, when I cube a negative 1, right, because this is really negative 1 times x, if I cube the negative 1 part, I get negative 1. So I can erase the parentheses, I don't need them, and I can erase these parentheses here. And all I want to do here is just divide both sides by negative 1, and this will cancel, and so will this, and I end up with my y is equal to, let me make that better, x cubed again, right? So these are the same. So that's how we know it's symmetric with respect to the origin. So that's kind of the easy way to look at it. The harder way is when we start involving this kind of function notation. This is where it gets super confusing. So we define this as f of x is equal to the negative of f of negative x. So this is one way to define it. And then another way is the negative of f of x is equal to f of negative x. So if your function has this property that the original function f of x is equal to the negative of f of negative x, or if it's the negative of f of x equals f of negative x, then it's symmetric with respect to the origin, and we could say it's an odd function. Now, these two kind of pieces of notation that you see are super confusing. What in the world does this mean? All it means is that for a given x comma y, you have the negative of that x and the negative of that y. So let me explain. Let's just take a given point. Let me just kind of start with this one, and then I'll work on the other one in a second. So let's say I take a point like, let's say 2, 8. We can see that here. So 2, 8 is our given point. Now, according to what I just said, it should be true that the negative of 2 and the negative of 8 should be on this graph. So negative 2, negative 8 should be there. If we look, negative 2, negative 8 is there. So we know that's true. But we can use function notation to kind of show this. All we're saying is that if I pick something for x and plug it in, remember, if I have something like f of 2, it's just the function's value when x is 2. So f of 2 we know is 8. So what is the negative of f of 2? Well, I know f of 2 is 8, so the negative of that would be negative 8. Okay, so that's this part right here. That's this part right here. Okay, so we know that's negative 8. And then a highlighting kind of maybe makes that not show up so clearly, so let me not do that. So then the other thing is, what is f of negative x? Well, if x was 2, the negative of 2 is negative 2. So f of negative 2, we already know that if x is negative 2, y is negative 8. So these two are equal or the same. Okay, that's all that notation is, just a fancy way to say that, hey, for a given x comma y, you're going to have the negative of x and the negative of y on that. You can also do it with that other notation that I showed you, and this is much less common, but you can also say that if it's kind of symmetric with respect to the origin, then f of x is equal to the negative of f of negative x. Again, just using that 2, 8 and the negative 2, 8 as a reference, f of 2 we know is 8. F of 2 is 8. Now, what is the negative of f of negative 2? Let's think about this. F of negative 2 is negative 8, but then I want the negative of that. Okay, I want the negative of that. So the negative of negative 8 is positive 8. So again, those two are equal. Now, graphically, we have to think about this a little bit differently. Let me go to the next page. it's not as simple to notice if something is symmetric with respect to kind of the origin as it is to notice if something is symmetric with respect to the y-axis or the x-axis. It's very clear that something kind of is symmetric with respect to the y-axis because the y-axis, again, it cuts it in half. Same thing for the x-axis, right? The x-axis would cut the graph in half. But with something that's symmetric with respect to the origin, one way you could do it is you could kind of flip your graph upside down, right? So this orange guy is the original. This is my f of x equals x cubed. If I flip that upside down, if I took my graph paper and just flipped it upside down, if I end up with the same graph, okay, then it's symmetric with respect to the origin. Another way you can do this, okay, if I think about the negative of f of negative x, we said this is equal to f of x. And I might lose some of you with this definition. But essentially, if we remember from the last lesson where we talked about reflecting graphs, if I had something like, let me erase this for a second. If I had something like g of x is equal to f of negative x, we know that g of x can be graphed by just reflecting f of x across the y-axis. So that's the graph I have here in light blue. So let's just say this is g of x. This is g of x, and it has this definition, okay? So I'm going to reflect it across the y-axis. And so for every given point that's on f of x, this orange graph, it gets reflected across the y-axis. So for a given y value, now every x is going to be the negative, right? So this guy right here was 2, 8. Now it's going to be negative 2, 8. This guy was 1, 1. Now it's negative 1, 1, right? So on and so forth. So from this point right here, we go to this point right here. From this point right here, we go to this point right here. So we end up with this kind of blue graph. So that's the first one. Now, let me further confuse you. And let's say that we had h of x, which was equal to the negative of g of x. What would this be? This would be what? If I want to graph the negative of g of x, well, then I just take g of x and I reflect it across the x-axis. Well, if we do that, what's going to happen? Let me kind of erase all this. Let me erase all this and let me draw that line back. Well, now I'm starting with the blue graph and I'm reflecting across the x-axis. So this point right here, we're going to have the same x value now, which is going to be negative 2, but the y value is going to be different. So we're going to have, instead of negative 2, 8, we're going to have negative 2, negative 8. Okay, so it gets reflected across the x-axis. Instead of negative 1, 1, we're going to have negative 1, negative 1, right? So on and so forth. So down here, instead of 2, negative 8, I'm going to have 2, positive 8. Instead of 1, negative 1, I'm going to have 1, 1. So what happens is all my points after I do this second reflection go back to the original graph of f of x equals x cubed. So now we see that this h of x ends up just being the original function f of x. And I know this gets confusing, so let me kind of erase all these different function names and just go back to what we really kind of started with and saying that, hey, if I took this guy, this f of x, and I reflected it across the y-axis, so I had f of negative x, and then I reflected it across the x-axis, so the negative of that, those two would be the same graph. They would be equal to each other. So that's how, again, we know that it's symmetric with respect to the origin. All right, let's look at another example of something that's symmetric with respect to the origin. So we have f of x equals 1 over x. And again, we can show this graphically, or we can also show this kind of with function notation, or we can show it just by saying that, y equals 1 over x. Again, by definition, I can replace y with negative y and x with negative x, because for a given x comma y, negative x comma negative y is going to be on that graph. So if I said I had negative y is equal to 1 over negative x, of course, I know that this guy, if I have a positive over negative, it's just a negative overall, right? So if I multiply this by negative 1 and this by negative 1, the negative cancels over here, and the negative cancels over here, and I'm back to my y equals 1 over x that I started with. So that's how I know this is an odd function, or again, it's a graph that is symmetric with respect to kind of the origin, okay? Now, another way you can show this is, again, with that function notation. You can say that f of negative x is equal to the negative of f of x, or you could say the negative of f of negative x equals f of x. I'm going to stay away from this definition for now. This is not something you really see in your textbook. This is just something I gave you so that you can see that if you kind of reflect the graph twice, you end up with the same thing, okay? So I'm just going to use this one. So f of negative x would be 1 over negative x. And if I had the negative of f of x, this would be what? I would just take the right side of this and just multiply it by -1. So it's the negative of 1 over x. These are the same, right? If I have a positive over a negative, it's a negative overall. I could really just say this is -1 over x. So because these two are equal or the same, we can say that we have an odd function, or again, we can say that we have a graph that is symmetric with respect to the origin. Now again, if I thought about kind of reflecting this guy twice, if I reflected it once across the y-axis and then again across the x-axis, you can do that on your own. You'll see that you end up with the same graph. Another thing you can do is just take your graph paper. If you sketch this, take your graph paper and flip it upside down. You're going to end up with the same shape. Okay, it's the same graph. Everything's upside down, but it's the same shape. But essentially that tells you that it's symmetric with respect to the origin. All right, so we can officially just say that an even function is where f of -x is just equal to f of x, okay? So if I plug in a -x everywhere I have an x in that function, and I end up with the same thing as if I just had f of x, we have an even function, or again, a graph that's symmetric with respect to the y-axis. Now for an odd function, you're typically going to use this definition. This is what's given to you in your textbook. The negative of f of -x is equal to f of x, or f of -x is equal to the negative of f of x. Now, for the odd function, again, this is something that's symmetric with respect to the origin. Now, you might be saying at this point, you know, hey, where's the thing that's symmetric with respect to the x-axis? Remember, when we deal with that, we don't have a function, so we don't have kind of a name for that because we're dealing with kind of functions here. We have an even function that's symmetric with respect to the y-axis, and then we have an odd function that's symmetric with respect to the origin, but we don't have anything that's a function that's symmetric with respect to the x-axis because those are not functions, right? They fail the vertical line test. All right, so let's look at these. So we have f of x equals 7x to the 4th power minus 2x squared minus 1. A lot of students will say, okay, I've got even exponents everywhere, so I know it's even. That's not always going to be true, okay? Certainly if you have just, you know, f of x equals x to some power, okay, let's just call that a. If a is even, then you have an even function. If a is odd, then you have an odd function. But there's all kinds of other things that can happen, right? You're not usually going to get something that simple, so you do have to go through and do the work. So for this guy, I'm going to start with f of -x and see what I get. So I would have 7 times, you'd have -x to the 4th power, minus 2 times, you'd have -x squared, and then minus 1. So I know in each case that this negative is raised to an even power, so this guy is going to be the same, right? So f of -x would be 7x to the 4th power, minus 2x squared, minus 1. So these two are the same, so this guy is going to be even, okay? And clearly it's not odd, because again, for something to be odd, f of -x is equal to the negative of f of x. Well, f of -x is this, right? This is f of -x. If I took the negative of f of x, this would be negative, this would be positive, and this would be positive. These two are not the same, so this function is even only, right? It is not odd. All right, let's take a look at another one. So we have f of x equals x cubed minus x squared minus 5. So I'm going to start out by seeing if it's even. So f of -x is what? So I have a negative x, and this is cubed, and then minus, I have a negative x, and this is squared, and then minus 5. So the problem here is that this guy is going to change signs, right? This negative that's being cubed, that's going to change signs, but this one isn't going to change signs, right? Because I have a negative that's now squared. So f of -x is going to be what? It's going to be negative x cubed, okay, then minus x squared, then minus 5. So this is different from this, right? Here we don't have a negative out in front. Here we do, right? The rest of the signs are the same. So we did change this guy, so it's not even. Is it odd? Well, for it to be odd, again, f of -x, which we have right here, should be equal to the negative of f of x. So in other words, if I multiply the right side of this by -1, well, I'd have a negative, a positive, and a positive. Those two don't match up either. So this guy isn't odd and it's not even either. So it's going to be neither. All right, what about this one? We have f of x equals x squared plus the absolute value of x minus 7. Okay, well, what do we see here? If I had f of -x, if I plugged in a negative x there and squared it, I know I just get x squared. Then plus, if I plugged in a negative x there, right inside the absolute value bars, I know I just have my x and then minus 7. So really this guy is going to be even, right? So this would be x squared. This would be the absolute value of x, and then minus 7. So these two are the same, so this guy is even. Okay. Again, you can quickly verify this is not odd because this guy right here is not going to be the same as if you had a negative f of x. Okay. These are not going to be equal. Let me kind of slide this down. Let me make this in a different color. So I'll put that this is even like this. So the negative of f of x would need to be equal to f of negative x. Again, we have f of negative x here. It's the same as this. If I multiply the right side here by -1, this would be negative, this would be negative, and this would be positive. Those two don't match up. So this guy is definitely not an odd function. All right, what about this one? We have f of x equals 5 over x cubed minus x. So what is f of negative x? This would be 5 over, you'd have your negative x, this would be cubed, and then minus, you would have your negative x. Okay, so first and foremost, we know minus a negative is plus a positive. So I can go ahead and just say this is plus. This is plus. And then if I take this guy, this negative, and cube it, I end up with a negative. So I can really just say this is negative x cubed like this. All right, so I know it's not even because this is different from this. But I can check to see if it's odd. So f of negative x should be equal to the negative of f of x. So I would multiply the right side of this guy by a negative. So really I would have what? I would have the negative of f of x would be the negative of 5 over x cubed and then plus x. Well, that's the same thing I have here. The negative's down here now, but I could move it up, right? A positive over a negative is just a negative overall. So these are the same. So we can say this function is odd. All right, here's a common one that trips students up. So you have f of x equals the kind of quantity x minus 3 squared plus 7. If you see an even exponent, a lot of people just assume that, hey, this is going to be an even function, okay? But in this particular case, it doesn't work out that way. Before we plug anything in, just think about this. If I plugged in a 5 there, 5 minus 3 is 2, 2 squared is 4. If I plugged in a negative 5 there, negative 5 minus 3 is negative 8. If I squared negative 8, I get 64. So that should tell you something's wrong, okay? So let's go ahead and erase this, and I'll officially do it. So f of negative x is what? Well, I'd have a negative x there minus a 3, quantity squared, plus 7. Well, if I went through and kind of expanded this, I could use my special products formula. So I could say this is what? This first guy gets squared. So now I've got to square the negative and the x. So that would just be x squared. Then I've got minus 2 times this guy times this guy. Now when we use this formula, we usually don't have a minus out in front. So you've got to account for that now, okay? Usually we just bank on this sign being whatever this is, okay? But in this particular case, it's 2 times negative x times 3. Those negatives are going to become a positive. So 2 times 3 is 6, so you're going to have 6x there. Then you get 3 squared, and that's 9. Okay, so then plus 7. So 9 plus 7 is obviously 16. So with this guy, you get x squared plus 6x plus 16. Okay, but if I expanded this one, we know that, let me kind of do this over here. You would get the first guy squared, which is x squared. You would get 2 times this guy times this guy. So 2 times 3 is 6. 6 times x is 6x, but it would be negative. So minus 6x. And then plus this guy squared. 3 squared is 9. And then your 7 comes along for the ride. 9 plus 7 again is 16. So these guys have a different sign, right? This is x squared minus 6x plus 16. This is x squared plus 6x plus 16. So they are not the same. Okay, so this guy is not even. Is it odd? Okay, is it odd? Well, if I go back to what I had, if I multiplied this guy right here in its expanded form by a -1, so if I had the negative of f of x, it would really be equal to what? It would be this guy right here. Let me erase this equals from here, and let me drag this down here. It would be the negative of x squared plus 6x minus 16. So this guy is going to be neither. It's not even, and it's definitely not odd because the negative of f of x is not equal to f of a negative x. All right, let's look at one more of these. So now we have f of x is equal to x times the square root of 1 minus x squared. Okay, so if I did f of negative x, this would be negative x times the square root of 1 minus, you'd have negative x squared. So you know inside here, this isn't going to matter, right? Negative x squared, that's just x squared. But it does change things because I have a negative here and no negative there. Okay, so these are not the same, so it's not even. Is it odd? Well, you can see that it would be, right? Because the negative of f of x would be what? I would multiply this thing by -1. So if I multiplied it by -1, I would just have negative x times the square root of 1 minus x squared, which is exactly what I have there. So this guy is going to be odd.